Recording in progress.
So that the density of white dwarfs is so high that you actually so high that you need take into account Pauli's exclusion principle. So the Maxwell-Boltzmann distribution is not applicable, and so we have to consider a fully degenerate matter distribution with t is equal to 0, right? And when we do that, so then we consider the equation of state, and then we look at the parameter x, which is equal to EF by ABC, right? So which is B by C. When x is much smaller than 1, then you get P goes as rho to 5 by 3. When x is much greater than 1, E goes to 4 by 3. Right? So this is the equation of state. And then I stopped at the mass radius relation. So because we are already seeing observationally that as the white dwarf the mass increases, the radius decreases. So which is a very curious property, and it's also very important from the point of view of the physics. Right? So here we considered the equation of hydrostatic equilibrium in an approximation, and then we got the quantity F. And then for the two cases of non-relativistic equation, we have got F goes as m to the 3, then C, f to the 1 by 3 into R, and for other F is equal to m to the 2 by 3. So here, if you want an equilibrium configuration, so F must be equal to 1. Right? So then what happens is that F is equal to 1. Then if you give me a white dwarf of a particular mass, then I can choose the radius so that this condition is satisfied. So that would be the equilibrium radius of the white dwarf. And the white dwarf will just go on existing for more or less forever, as I'll describe to you later. But then as you keep increasing the mass, then you pass from the non-relativistic to the relativistic domain. In the relativistic domain, you go to the other equation. So F is equal to F goes as m to the 2 by 3. So which would mean that when you have this result, it would mean that there is a unique mass. Because I cannot now choose the radius. This mass is given to me. And this is the only possible equilibrium configuration when you have got a relativistic equation of state. And so that tells you that something drastically new which has appeared on the horizon. So what I want to do now is again to use the principles of quantum mechanics to derive the expression for this unique m which is present in the relativistic case. Okay, so this will be the last step in coming to the steady-state equation. So you see that we have got the uncertainty principle, and delta x is the delta p. So we want to apply this to an electron gas which is inside. Because as I told you, that there is a gas of the nucleons. If it is a pure hydrogen case, then it will be protons and electrons. Otherwise, if it is an evolved star, so then you will have hydrogen and helium. So there will be protons, and then there will be helium nuclei, and there will be the electrons. But because the proton mass and the nuclear mass is so much higher than the electron mass, those will not become visible. And so we are only concerned with electron gas. And so what would be what is delta x? We want a representative number for delta x. And that is clearly the interparticle distance. Right? Because we know that in that much of an L there must be one particle. And that's the spread of the particle. Right? So we take delta, sorry. So we we take delta x to be the interparticle distance, which as you know is equal to -1 by 2. And what is the momentum? The uncertainty in the momentum, the representative number is a characteristic momentum of the system, which as we know is a Fermi moment. Right? It's clear. So we have got n to the minus 1 by 3 into Pf is equal to h cross. So, so then Pf is equal to h cross n to the 1 by 3, which is h cross n upon Rk. You get this? Because n is a particle number density, capital N is the total number of particles. Then obviously a factor of 4 pi here, but 4 pi raised to 1 by 3 is not too large, so we just forget it. Okay, so then we have got h cross into what is n? N is equal to m upon, which is because n is a particle number. So that is equal to mass upon the average particle velocity, which we take it to be the total mass. So this becomes h cross n to the 1 by 3 r upon nt to the 1 by 3. So now, what is the pressure of the gas? The pressure of the gas is equal to the particle number density into the velocity into the momentum. That's what you learn this from the kinetic theory classes. So this is a relativistic gas. So V is approximately equal to C. So the pressure is equal to NCP. And so FP is equal to pressure by N is equal to H cross C N to the 1 by 3 R to the 4 NP to the 4 by 3. I just put it together whatever happened on the previous slide. So now what is Fg? We are deriving an expression where what is Fg? It is simply Gm squared by R. Yeah,
Fp was pressure by R.
Pardon me?
Fp was pressure by R.
That's right. P, even though it's P by L. The P by L. Okay, let's go back and look at it. So, oh my God. The crazy thing. It goes very fast. P is P by L. You see that? Yeah. So we have got Fp and what is Fg? It's just G m by R to the 4. So Fp is equal to Fg for equilibrium, means that you are equating these two expressions, and you get m to the 2 by 3 is this, and then m is equal to h cross c e upon np square 3 raised to 2.3. And so you see, it has come out like magic there. And this is not the way Chandrasekhar derived this expression. Okay, Chandrasekhar always did things in a very, very exact. And so I'll just introduce you to his way of deriving these things. But I believe that this derivation, I wanted to lie down. There's something, you can zoom from my, and I thought that just zoom झाले थोडं कमी करता येतं आता हे पूर्ण दिसायला पाहिजे स्लाइड दिसत कसं करायचं माहिती नसलं तर आपण पुढे जाऊया प्रॉब्लेम झाला नाही बोलू नका जाऊ दे बघूया बाकी तर ठीक आहे so you see that we don't want to consider, I don't want to do this in any detail, but this is Chandrasekhar's theory of white bars. And so how did he do it? So you see, you've got here rho is this, and he puts it as x is equal to c, and get PE, the pressure, is C1, which is this quantity, into Fx. It's not बाकी तो ठीक है हर zoom झालेलं आहे okay. So I'll come back to this slide at the end of the lecture. So, so you see that you remember that this was the expression for Fx, which we got when we derived degenerate, perfectly degenerate gas. Right? So, and then we know the two limiting cases, but we are not going to put the limiting cases. So what happens is that you've got dp by dr, which is written in this particular form. Okay, then you've got Poisson's equation. Laplacian phi is equal to 4 pi g. And because it's a spherically symmetric object, this is the Poisson's equation. Right? And then you've got here certain changes of variables something. Right? And then you get this equation. So this is the equation for the hydrostatic equilibrium, the structure of white dwarfs. Absolutely no approximations are there. There's just these transformations which make this equation convenient. So you see that Chandrasekhar was a great master in introducing these new variables. I mean, here it is completely trivial. But I mean, if you look at his books or papers, it makes a fabulous transformation. And the thing which I know, I mean, I'm not studying it, but I know he will, is that you must have studied the Schrodinger equation. And then how do you solve the Schrodinger equation for the hydrogen atom? You can separate the right? Because of symmetries. So you get psi r, okay, and then you get this p theta phi. And then p theta phi, you know how to solve that. And then in geometry, a radial equation which is solved. And what is important is separating it. So now you have heard of the Dirac equation, okay, which is the Dirac equation of the electron. So now, if you try to, you can put the Dirac equation in a form which is valid for curved spacetime. Because the normal Dirac equation is its special relativistic equation. It is for flat spacetime. But you can write out the Dirac equation with curved spacetime. At which point it becomes pretty complicated. And then there are lots and lots of people who did approximation solutions of it. It's so complicated that you couldn't really solve it properly. So there are lots of the friends of mine who did the PhD thesis getting approximate equations of that. And then Chandrasekhar at a very late stage in his life started doing the derivatives. Okay, and so then he looked at Dirac equation and he just put new variables and separated it. Okay, so just one page paper. So the moment he separated it, he could solve. So he had a great technique for that. Right? So you have got this straightforward looking equations. And what are the boundary conditions at the surface? Phi is equal to 1 and d phi by d psi is equal to 0. These are the boundary conditions. We are not going into details. So now, using that, you see that you can get an expression for r by integrating it adequately, and you can get an expression for n. So once you've got an expression for m and r, okay, but you see that there's a r here. So you get a mass radius relationship for that. So then now you can't solve the equation analytically. But this is not from Chandrasekhar's original thing. I'll show you that in a moment. There's a very beautiful book on stellar structure by Kippenham and Wieger. And you see that there all these things are given. Right? So you've got N, you've got R. So you've got the mass radius relation. And we know approximately that R goes at N to the minus 1 by 3. Right? So now here's a plot of N against R. Right? So you see this is the exact thing, meaning that you are not solve the equation exactly, but the exact equation is a numerical solution for it. Right? So then you see that as you go on increasing n, then r goes on decreasing, and you can get your approximate relations from that. And then when you come to this specific mass, radius phase goes to 0. Okay, so that mass here is a Chandrasekhar mass. Okay, so and how much is that mass now? So it is m Chandrasekhar 2 upon a mu e. Mu e is called the electron molecule. And if you have got anything which is heavier than hydrogen, helium, and so forth, then mu is always equal to 2. And so therefore we get Chandrasekhar equal to 1.4 times the solar mass. Right? And then here, this is actually from Chandrasekhar's book, and he did these calculations. And at that time, now here it will be completely trivial. And you just call the Python routine and you do the calculation. So here you have to do it with cranking the calculator. So we did that, and you see here, the important thing is that this is the mass, And here you go up to a high level of mass. At that point, the radius is zero, is infinity, and density is infinity. And so then the question is, what happens when you actually reach that stage? Then it starts collapsing. And what happens to it afterwards? Then Chandrasekhar didn't say anything about it. He says, I don't know. And he said, that's for the future. And so this is the curve which he had drawn. For that, you see that it just collapses to zero. Okay, so what is the actual structure of the white dwarf now? So if you look at it, we have seen a radius of approximately 6,000 kilometers. And then what happens is that this matter here is fully degenerate. But as you come to the top, to the surface, then it is no longer fully degenerate there, and you've got a thin layer, a thin atmosphere of the white. Okay, so which is not degenerate. Now, so let's just see from the modern point of view what happens when the collapse proceeds. So you are aware of stellar evolution, I'm sure. Right? So what happens is that in the initial stage of the star, in which the sun is, there's hydrogen, it's mostly hydrogen, 25% helium. At the center, there is the fusion of hydrogen. And you get a thing where you get a helium at the center, and then you are got surrounded by mostly hydrogen. Then, then you get to the next stage. So if you exhaust the helium at the center, okay, then the temperature will start decreasing because there is no longer any generation of energy. The energy keeps going up, and therefore the temperature will start decreasing. Because decreasing temperature, there's decreasing pressure, and because of that, there's collapse of the central part, right? And then which releases energy, and the outer part gets expanded, and that becomes a red giant. See the red, so it expands quite a lot. The inner part keeps collapsing. Now there are two possibilities. One is that the mass is lower than the mass of our sun. Okay, let's say half solar mass star or something like that. Okay, then the collapse continues and there's nothing to stop and it will become a white dwarf. And the outer part will go off in an explosion. Because we have seen that the binding energy is about 10 to 50 ergs. And so that is, I think that goes off in the explosion. Now, if on the other hand the mass is sufficiently large, then the temperature at the center will be sufficiently high, and so you ignite helium. When you ignite helium, then you start getting carbon, nitrogen, oxygen, and so forth. And so then again it becomes steady, but it is no longer on the main sequence. Because you have to be on the main sequence, you have to be burning hydrogen at the center. But here now you're burning helium. So it just moves a little bit out of the main sequence. And so the main sequence becomes thick rather than just one single line because of that. Then you go on doing this. At every stage of fusion is complete, the inner part contracts, the outer part expands, and then you get a further cycle of fusion. So if the star is sufficiently massive, meaning more massive than about, let's say, 15, 20 solar masses, okay, then you'll go right up to iron. And so you get iron and then progressively less heavy elements which are coming into the outside. And you know why you cannot go beyond iron? Yeah. Okay, because the peak is the binding energy comes. And so now here you see that we are starting from the main sequence. And each time that there is a new fusion sets up, then the star expands and it contracts, expands, contracts, until if you go the whole way, then it will get supernova explosion. So this is the first possibility, that you get to form a white dwarf at the end of the matter, and you get the outside is known as a planetary nebula. So this particular one, the very big structure, big nebula, is quite close by, 2,300 light. And then, if the star is sufficiently massive to go up to iron, then you get an explosion and then you get a supernova. And these supernovae are extremely important for everything, including our own existence. So that is because you cannot synthesize elements heavier than iron at the center of the stars. And it's only when you've got a supernova explosion that you can actually have sufficiently high temperature for a very brief period when you make the heavier elements. But still, people were confused as to how can you make. They did not know how you can make gold and platinum. And I don't understand why specifically those two elements, but it's a question of the detailed atomic and nuclear physics. And then it was speculated that if two neutron stars they merge into each other, then you get gold and platinum. And you must have heard that LIGO actually detected a neutron star merge, a binary neutron star merger, and they did see gold and platinum. So that is where it all comes from. It looks like a very exotic process. They will first need to make two neutron stars and then they need to spiral, emit gravitational waves and merge into each other. But that is what it takes to make platinum. Right. So the thing is that what is most important in all matters of stellar evolution is the initial mass. Right. So that practically determines the history of what the entire history of the star. And apart from the mass, the chemical composition is also important. But this is the main determinant. And so you see that very small initial masses. If you take an object, suppose you have a perturbation, and then the object starts collapsing. If the initial mass is at 1/100th of a solar mass, then you get a planet. Then in the next stage, you get a brown dwarf. And a brown dwarf really doesn't have enough mass to actually have nuclear fusion. But a brown dwarf emits stored energy. And also there's a trace amounts of fusion which take place. And then you get the next one is the lowest mass stars. And then you will end up as a helium white dwarf. Hydrogen to helium, nothing more than that. Then the next one is carbon, oxygen, nitrogen, etc. All these give planetary nebulae until you get to this range, about more than 12 solar masses, you get a neutron star. And about the mass is greater than 40 solar masses, star will get a black hole. Point is that all these black holes will always end up as so that they end up as relatively low mass black holes, meaning less than about 15 solar masses or so. Right? But the first black hole binary, the first detection which LIGO made, were two black holes which were spiraling in each other. And they were much more massive than anticipated. Something like, I'll show that. Okay, in my next two talks, I'll show you that much of the mass. And you must already covered by Sanjit also. And that mass is very much higher than first people thought is possible for stellar mass black holes. So that's still other people are working. Okay, so now we come to, as I said, I want to cover two aspects. Okay, one is the cooling of white. So why the cooling of white dwarfs? Important. And then look at the sun. The sun has got a surface temperature of about 5,800 Kelvin, and it has got an internal temperature of, I think, 12 or 15 million. And if you do it in a high grading way, you get 20 million. Now that temperature has remained incredibly constant. Okay, because we know that there has been life on Earth for a few billion years at least. Okay, maybe 4 billion years. A very, very primitive life it existed. And we know that primitive life can exist at higher temperatures than we can exist at, but not much higher temperatures. So that tells you that the sun has remained as it is for an extremely long period of time. That is why it is perfect hydrostatic equilibrium, and the amount of energy which is generated inside is all transported outside. Okay, otherwise there will be big trouble. And so, but now if you look at a white dwarf, there is no energy generation which is taking place inside. And they can always be traced. When you say no, these are not absolute no's. There is some little bit of thing happening here and there, but for all practical purposes, there is no energy generation. And so which means that you've got a hot object, very high temperature, even though for our physics purposes we're taking to zero, very high temperature, and then that is radiating. And so as it radiates, what happens to it? It was cool. Then the temperature will start going down. Right? And then, so if we try to study the process where the temperature is going down, you find that you can get a very good relation between the temperature, the current temperature of the white dwarf, okay, and the age of the white. Okay, so yesterday somebody asked me about the spectrum of a white dwarf. So you can see the spectrum, and then you can estimate the temperature of the white dwarf from that, right? And then you know the age. So if you look at the distribution of white dwarfs in the galaxy, and then you get the distribution of ages, because that tells you about the history of star formation, right? Because from the type of white dwarf, you know what kind of a star it came from, and from the age, you know when it was formed. And so you can trace the history of star formation in the galaxy by looking at the current distribution of white dwarfs and the temperature distribution. Right? And then it turns out, as usual, that it's pretty straightforward to work it out. Have you heard of the William theorem? Somebody has done it for you. Okay. So, just I'll quickly run through. What the William theorem tells you is that the total internal energy, okay, so two times the internal energy plus the potential energy, gravitational potential energy is equal to zero. And to what kind of an object does this apply? It applies to an object which is in equilibrium, hydrostatic equilibrium. But you can consider a situation where you can slowly squeeze that object. Okay, so it is not in, if it is full equilibrium, it maintains the same size. But let us suppose that the object is slowly contracting. So you've got a primordial cloud of hydrogen and helium, and then you want to form a star out of it. So that will happen when the cloud will be contracting very slowly. Now, very slowly meaning what? Is it 1 kilometer per second or is it 1,000 kilometers per second? So you need to, whenever you say slow in physics, you have to say slow compared to. I mean, when you are doing relativistic, non-relativistic, it is slow compared to speed of light. Okay, but here, does anyone know what slowness means? So look at the situation. The situation is that you have got an object which is nearly in hydrostatic equilibrium, but which is collapsing very slowly. Okay, so now slow compared to what? See, you have got the speed of light. So what would be the analogous for making adjustments in the gas? Yes, speed of sound. Okay, because see, if I just push hands like this, then the air here is very compressed and the wave is going. And at what speed is it going? It's going at the speed of sound. Right. So as a star keeps keeps reducing in size, to compressing the star, there is pressure imbalance, and that pressure imbalance has to be smoothed out. Okay, and that would happen at the speed of sound. So if you have got an extremely fast collapse, okay, then it will not be equilibrium. And when a supernova explosion takes place, it's the opposite of a collapse. There's an extremely high shock wave. Right? But if I make sure that the velocity of collapse is much lesser than the speed of sound, then what will happen is that as the pressure imbalances occur, they will spread out at the speed of sound and it will always remain. So when you talk of an adiabatic collapse, that is what you mean. Right? It is always smaller, and then the velocity of collapse is smaller than the velocity of sound. So when that condition is satisfied, there are two K plus V, which means that the internal energy is equal to minus half the gravitational potential. And you know that the gravitational potential energy is negative. And that is why you have got the negative sign. And the total energy, which is K plus V, is equal to E is equal to V by 2. So now what the sign of the total energy then? Negative. Because there is a binding energy. So you need, if you in collapse, so much energy has been released in the collapse of the. Right. So now if I change the radius slightly, then all the quantities will change. And delta K is equal to minus delta V by 2. And delta is equal to delta V by 2. So you see that this is all crazy. If you look at it. So this is the internal energy. Internal energy associated with the temperature. So now I'm having a collapse. And because of the collapse, the temperature increases. So you get that? Because of the collapse, the temperature increases. And so the internal energy is increased. But what happens to the total energy? it decreased. And so this is why it's called negative specific. If I want to heat this one, then I have to supply energy to the goes up. But here you are extracting energy from, and the temperature is going down because of the collapse and because gravitation has negative. So where there's a difference go? Because the total energy must be conserved. Okay, here the total energy coming minus delta V by delta V by 2. So minus delta V by 2 has actually been emitted. Hence it goes out as radiation. So if the collapsing cloud, then it will go to infrared radiation. But as it gets hotter, then it will become like a star. Right? So this is this will use it. Now that's a cooling of white dwarfs. So they already covered this. White dwarfs cannot generate energy through nuclear fusion. Right? And then the energy that they emit must come from stored thermal energy. But there are also other energy, as I told you, and you can look them up. But there are 3, 4, 5 different methods. If you like, I can give you further references. Okay, so therefore the white dwarf will always cool over a period of time. I mean, unlike a main cyclic star, for example. Okay, now in a normal star, energy is transported by radiation and convection. Somebody told you about that? Yeah, this stellar structure and evolution. By it has convection and but the energy is not transported by convection. So can you guess why that is? See, when you say that, let's say that what happens is energy is transported by radiation. So there's hot matter right at the center of the star. A photon is emitted, which is at 20 million Kelvin, and it has to make its way out. Now, as it starts making its way out, it will hit an electron. Okay, then it gets scattered. And it is scattered backwards, forwards. So it slowly has to diffuse out. And do you know how much is the mean free path? You might imagine what the mean free path is because let's go to 7 into 10 to the 10 centimeters. But the mean free path is just about a centimeter. So if the photon is immediately after emission is absorbed. Okay, but then the atom will again emit other photon. So like that. So you can imagine that the photon is just random walking its way. Okay, so it's a mean free path which determines the range at which energy starts going. And it turns out that you cannot have, so this is also the transport of energy by radiation inside matter is exactly analogous to the transport of energy by conduction. Okay, so you see that when I first heard these names like radiation and convection, etc., in high school, it was very simple. The radiation, conduction, and convection. Right, so radiation, that was too difficult. Convection, nobody told us anything. Conduction, we had to do this experiment with a rod and the temperature fall, and that never worked. So I thought it was all extremely funny. But when you actually look at the physics of it, it's remarkably good. Because the equation which actually tells you about radiation transport, okay, is exactly the same as the equation for transport of conduction, transport by conduction. But radiation transport occurs because of photons, and conduction occurs because of electrons. And because of the very high density inside in a star, the electron mean free path is so small that there is no conduction which takes place. But you remember that now we have got degenerate matter in the world. Okay, so all the low energy electron states are occupied. Right, so therefore, if you got an electron, it cannot go to a lower energy state at all. It just keeps moving. Because there's no place for it, there's no way in which it can go to lower. All the energy states are occupied. And that increases the mean free path drastically. And therefore, conduction is the sole energy transport, the most important energy transport in particles. And then it is so efficient. I showed you a picture of the white dwarf. The whole thing is more or less at a constant temperature. So you got an object at constant temperature. Ordinarily, that would not have been at hydrostatic equilibrium at all. But here, the equilibrium is not because of the pressure related to the temperature, but because of these lattice. Right? So what happens is that conduction takes place by conduction. Electrons can travel long distances, And then, because the conduction is very efficient, the interior of the white dwarf is isotope. Okay, and then you've got this thin, non-degenerate atmosphere around. Okay, so so let us look at it. What is the thermal energy? And from the visual theorem, we know it is P by 2, which is half Gm square. So now the thermal energy I know is equal to 3 by 2 Nk. So, and what is N? So I'm considering a hydrogen and a helium white bond. Okay, so I've got 4 nucleons and 2 electrons. And so because all the hydrogen has been converted into helium, the outer parts have been thrown out. And so the white dwarf is principally helium, right? Plus electron. So therefore you have to put in this factor of half and 1 by 4 in the mass. And then you get thermal energy is equal to 9 m kT by 8. And then if you equate these two, you'll get kT is equal to this particular expression. And you know that you should have been able to write this out directly because I got the electron there and the thermal energy is kT by 2 and this is the potential. So that is what this equation is saying. So because I know that R goes to the m minus 1 by 3, so therefore kT goes as m to the 4 by 3. Now, all there are missing constants here. I did not put them in because they are too, it become very complex expressions with the constant. So, but if you take a half solar mass white, then kT is equal to 70 keV, which is equal to 8 into 10 K. And so that is the temperature of the white. So then, so now the energy radiated from the surface of white dwarf is a thermal energy of a classical gas. You can neglect that. You just imagine that it's at a very high temperature over the degenerate object, and that is radiating out into space. Okay, and the radiative energy loss is obtained by equating the black body luminosity to the rate of thermal energy. So when you do that, so you've got L, which is simply the Stephen-Boltzmann law, and then that is equal to the rate of change of thermal energy. We know what is the thermal energy, therefore we get dT by dt. So now you see that you have got dT by T here, then the power of T. It's going to be extremely easy to integrate that. And then the net result is this T, that the age of the white dwarf is now related to the temperature. And you see here, very, very simple relation. So if you have got a white dwarf, which is about 1000 Kelvin, so which means that it is 3 billion years old. So, and then if you give me the age, I can give you the age. And so, now the detailed model, you see that you've got the cooling time up to the upper limit because of various approximations there. The shell has an effective temperature significantly lower than the interior, which also we have considered. Okay, and this lowers the cooling. So the cooling rate that you have got is an upper limit. And detailed models show that white dwarfs cannot cool to below 3 to 4 kilokelvin. So what does this mean? Is that you form a white dwarf, then go on cooling, and the universe is getting older and older and older. And then white dwarfs will get, but they are not going to cool, they're not going to go to 0 Kelvin. They are going to remain at the temperature, and the coolest white dwarfs known have the effective rest at 35 Kelvin. And so there's I don't know whether you have heard of him, but the great physicist called Freeman Dyson. So, he's one of the creators of the quantum field theory, quantum literality. And I've heard him giving a talk in Cambridge. And because I think that was 300th anniversary of Newton's principle. Okay, and then he gave a talk. And then we were talking about what will happen to the universe after this. When the universe goes on getting old and old, the white dwarfs are there. And then according to him, all the particles start decaying, photons will decay, everything will happen. And finally, if you assume that neutrinos are massless, then the whole universe will be converted to neutrinos. So, but this of course is much more. All right. So now I go to the last part of my thing, and which is white dwarf distance. Meanwhile, does anybody have questions?
White dwarf age you're talking about, that is the age of the star since it became a white dwarf?
Yes. Okay, so T is equal to 0 is the time at which the white dwarf was created. Okay. But as they get older and older, it really doesn't matter. I mean that age will be much more than stellar. But not if it's a half solar mass. So if it's a very low mass star, then then you see that their age, once you form them, their age can be longer than the age of the universe. But the universe is infinitely old, then it's all right. Okay, but so that was one of the things of the Hoyle, Professor Nalika's Hoyle Nalika predictions. Is that if you get really, really old objects which are much older than the Big Bang, so they must have come from a previous cycle of universe. All right, and now the last one is white dwarfs and distance measurements. So, are you aware that white dwarfs can be used to measure distance? They're extremely important. When you say, for example, not dark energy, what the other one? The cosmological constant. Okay, so there, when you want to see whether a cosmological constant exists, and then yeah, dark matter and dark energy, and then it is white dwarfs which become the distance indicators. Okay, so the people who did the observation, they got the Nobel Prize. So let's see how do we get to white dwarfs? So they have got, you know what is supernova, and there are different kinds of supernova. Okay, and this the transcript is actually very straightforward. So there's supernova, and then you look at its spectrum. And if you find that there are hydrogen features in it, just ask, are there hydrogen features in the spectrum? So if it is yes, then it's called supernova type 2. If the answer is no, then it's supernova type 1. Right, so here you can see, then you can go into other types of supernova. We follow this branch, supernova type 1, then does it have silicon features? If it has silicon features, then it goes supernova type 1. And then there are helium features, and helium features exist or not is supernova type 1b and 1c. And what we are interested in is supernova type 1a. Okay, so let's see why we are interested in supernova type 1a, talking about white dwarfs. So we already see that the classification depends based on spectroscopic features. And the spectrum super 1a, the light curve shapes and absolute magnitudes are remarkably homogeneous. So you look at the 100 supernova type 1a, look at the light curve. You know what's a light curve for supernova? So it just takes off. The brightness keeps increasing as the supernova develops. Okay, and then it goes into a long decline. And so, for example, when you are looking at the crack nebula now, it's no longer called a supernova. It is a remnant of a supernova. Okay, so the light will, all sorts of evolution which takes place. Okay, so this is a light curve of a supernova, a specific supernova. But what you can do is that you can take lots of supernova type 1a and combine them all together and get the average light curve. And have more or less the same shape. Okay, so you see that there's a very rapid rise, and then there's a rapid decline up to some point, and then a more gradual. So rise to maximum light in about 20 days, with absolute magnitude at maximum is minus 19 points. And so this is a fantastic case because you see that the moment if a supernova goes off in a distant galaxy, all that you need to do to take a spectrum. And in the spectrum tells you the supernova type 1, then you know what is absolute magnitude. So if you know the absolute magnitude, you know the luminosity. Right? And then you know what the observed flux. Right? So therefore, is it clear to you that you can get the distance? Because the total luminosity L. So the total luminosity L that you have, that is equal to 4 pi into distance squared into 4. Right? So your distance simply is equal to L upon 4 pi squared plus. So what's the deal there? Look at supernovae and from the spectrum determine whether it is supernova type 1a, then you know the absolute magnitude, therefore you know the flux. Then, of course, lots and lots of different steps involved. I mean, it's not as trivial as we are saying it here. It's a big technology which is involved there, but you can do this calculation. And so, so then, the homogeneous properties indicate that it's a unique class of perfume. So this is very important. So if all supernovae type 1A have the same property, then it stands to reason that they're made in the same process. And so the question is, what is that process? So there you see, when you consider different models of making, it turns out that the most possible model is where you have got wide valve with nearly Chelsea characteristics, just less than say 1.38 solar mass or 1.35 solar mass. If you've got an object like that, you dump some matter on it. And what happens to the object? It just collapses. Okay, and when it collapses, you release 10 to the 50 hertz and you get it as simple as that. So, but now the problem is the following. Because you see, the astrophysics itself could be an interesting subject. You just get a solution, you say, okay, dump matter is there. But most supernovae, most white dwarfs actually have 85% of the white dwarfs are mass less than 0.8 solar mass. So I told you that there are very few white dwarfs that are actually at the telescope. So which means that for you to have this mechanism, you need to pump up a white dwarf to nearly the telescope. So how do you do that? So do you have any idea how that is done? Have somebody told you about mass exchange that takes place in binary systems? And so if you put it in a binary system, okay, then it can get mass from the companion and it can grow in size. And so, so you see that this is what you have got here. So you have got let's say that you've got a white dwarf, and then you've got a large star, and then matter flows from the large star into the white dwarf. Its mass keeps increasing, and then it will gradually exceed its velocity. So let's see what is actually involved here. I'm sure somebody else. Have you heard of Roche laws? Yeah. And you know that the Roche laws are the trees. Yeah. Okay, you have seen all the Lagrangian points and so on. They're in the trees. It's pretty well done. You see, the story for that is when we were building IUCAA, we transplanted lots and lots of trees. Not a single tree was cut. Okay, so 40, 50 years, all the banyan trees you see everywhere here, they were more or less where this building is. Okay, and then they were all lifted and taken. There was somebody who had done it for Homi Baba and he did it for us, lifting these trees. We forgot to transplant those two trees. Okay, so when that courtyard was ready, then I was talking to the architect called Charles Korea, and he said, these trees have to go. And he was a very tough guy. I said, these trees are not going. Okay, so then he said, tell me what to do with them. Then I said, let's treat them as two stars. Okay, and then we put the Roche roads. Okay, then we got the Lagrangian points and put them. So it was purely accidental. It was not deliberate, but it has come out to be a very nice construction. So you see, the point is that if you've got a single star, spherically symmetric, then the equipotentials will be spherically symmetric. But if you've got a star in a neighborhood, then if I've got a particle here, so this particle will be attracted by this star as well as by that star. Okay, so in effect, it distorts the potential. But there's an added effect that you're going to take into account. That's because the two particles cannot just sit at a fixed distance from. If they are to maintain a fixed distance, they are going to orbit around each other. So which means that there is centrifugal force. And because of the centrifugal force, there's a distortion of these things. So you can imagine that it becomes like this, and this becomes like this. And at this point here, you're going to Lagrangian potential. And so if you are on this side, you're pulled here. From that side, you're pulled there. But if you're precisely sitting here, okay, so then there's a minimum in the potential, and the result of it continues stability. Okay, so you must have heard of the Aditya mission in Lagrangian. It's Aditya L1 because Aditya L1 is going to go to the first Lagrangian point, which is 1.5 million kilometers. Right? So now you don't actually sit there. That's the idealization. Well, you can go into an orbit around. So which is what Ajit tells you. And so, and then as far as we are concerned, the beauty of it is that if the star is living deep inside the rose core, but as the star evolves, it becomes a red giant. Okay, then it can fill the rose. And so if you look at the matter which is touching the rose core here, so these three forces cancel each other. The two gravitational forces and then the centrifugal force they cancel each other. But there is one force which remains unaccounted for, and which is the pressure. And so therefore the pressure forces the matter to go to the other star. And because it has got angular momentum, it goes around and it will form a pressure disk. Okay, so this is what you are seeing in this picture. So the stream coming in from the Lagrangian point and it forms a, it just keep going round and round and spirals. And so, so then now you see that you can have this evolution where you're going to have a more massive star and a less massive star. And then small massive star evolves first. Becomes a red giant, it can pump matter into the other one. Right? And then you can have other things like this one also evolves, and then you get what's called common nebula. So this was a great puzzle because there were some binary systems in which the more evolved star is a less massive. Okay, so this is how can this happen? Because you know that the more massive the star, then it should evolve faster. But here, the more in a binary system, the more evolved star is less massive. And so I believe that Fred Hoyle and then a young graduate student, they they gave the explanation at the same time. They said the mass exchange is taking place. And so what happens here in this kind of mass exchange is that this is a more massive star. And therefore it evolves first and forms a giant. And then the mass pours into the other one. And so when mass pours into the other one, then this can become more, it can become more massive. And at which point this can explode. Okay, so let's go to this one. How do you form the kind of boundary required for for an accretion-induced collapse? It's called AIC, accretion-induced collapse. And so you see that you're got a binary. What's a primary star? A primary star is more massive. Secondary star less massive. So this evolves, and then this transfers enough matter into it, so that this becomes more massive. This becomes less massive. Okay, and then this evolves, and then it, now this is a white dwarf. Okay, this evolves, and then it transfers matter back to the white dwarf, pumps it up to the Chandrasekhar level, after which it is collapsed. So this may seem like a very unlikely scenario. Really, am I just putting things together artificially to say that this is what will happen? So actually, this kind of a thing was first done by somebody called Ed Van Hoyle. So he's a Dutch astrophysicist. And then there were many new kinds of objects which were being discovered. And then, so they had to apply this. You see, what happens is that, you know what's an X-ray binary. And so, the X-ray binary has got either a neutron star, okay, or a black hole. And then the other star is looking matter. Now the problem is that when you form a neutron star or a black hole, right? So then you must, if it explodes, the star explodes, it loses a lot of matter. Now you can show with a very simple calculation, if you can try to do. That you got a binary with two stars N1 and N2, and then if the more massive binary explodes, then the system will disappear. Why does it integrate? Because you can show that the binding energy will become positive. Okay, the binding energy is no longer. So then, how can you have a neutron star binary? Because it must be a more massive star system. So then you say that the mass has gone to the other star. So I am evolving, but I pour matter into the other star. My mass becomes less than the other star, and then I. Okay, so there are a lot of subtleties which are involved here, and so you see that finally you end up getting a supernova type 1A because there is an accretion-induced collapse. And so now there's also another interesting variation possible, which is called the double degeneration. Because we consider we're considering a thing where we've got a white dwarf and another star. but there can be two white dwarfs separately. Both are degenerate objects. And so it is like a neutron star line, which you have already observed through light. So here you have got two white dwarfs, and then they go on. You see that they are very compact stars, and they will be very close binary, and therefore they emit gravitational radiation. As they emit that, they lose energy and then they collapse further. And then they can just merge into each other. Two less massive white dwarfs, they fill their own Roche slopes, okay, and then they form a disk, and then they merge into each other, and then that. So this is one thing which is possible. Two white dwarfs which are parallel in each. So now, the diagram, it's a Hubble diagram, the type of supernova. So you see that when Hubble first did his calculation, the first diagram, they were right in this area. And so now we have got a redshift of, and at that those distant redshifts, so these are all these are all supernovae one-way observations. And you see that this is from the low redshift supernovae. This is the Sloan survey. Okay, then the Pan-STARRS survey. These are all surveys which go deeper and deeper, and then you've got the HST observations. That's so you see how beautiful the thing is. And the deviation, you can plot the deviations from it, and these are different values of omega lambda, there's the dark energy component and the matter component, and you find that 0.7, 0.3 fits the thing. So that is why you feel that you have demonstrated the existence of dark energy. Right? And white dwarfs are very critical. Okay, I'm done. Any questions? Yeah?
The white dwarf calculation we took temperature of 0,
Yes.
but you were showing it.
Yeah, I'm sure. Brilliant. Yeah, you see, what I will do is that I was going to do that calculation today. I forgot to do it. I'll do it tomorrow for you. So there are two things which are involved. So first of all, t is equal to 0 is the idealization. What you are actually using is a Fermi-Dirac statistics. And the Fermi-Dirac statistics has got what called the chemical potential. Right? And so, and which is nothing other than the Fermi energy that we talk. Okay, so you can show that for all these, even though the temperature is so large, because the density is so large, you can show that T upon the Fermi energy is much smaller than 1. Okay, and when that applies, when that approximation applies, then I put in T equal to 0. You can assume that it is a fully degenerate gas. Okay, but just like we made this approximation that P goes as rho to the 5 by 3, P goes as rho to the 4 by 3, then Chandrasekhar's theory can do it without any approximation to get the full rigor of the thing. So here, there's something called partial degeneracy, which I mentioned yesterday. Okay, is that when T is not actually equal to 0, there are some of the electrons will have more energy, and then they go outside into the Maxwell-Boltzmann zone. Right? So you can take partial degeneracy and redo all the things. But it's a very important question to ask, and a very important concept to know, that it is a comparison of the temperature and the temperature. Yeah.
Answer about the P by MC that we substituted.
Yesterday you asked a question. Yeah, what was the question actually?
So we assume that P by MC is much greater than 1.
Yes.
How can the velocity?
Here. Oh, there's a question which is coming up. Let's see. What's your question? Is that Here X, right? This one.
I think it was another slide, but yes, X.
X.
Yeah, yeah.
Right? So now you see the Furby momentum, right? And then when X is much greater than 1, what is the expression for momentum? See, just LV. So when X is much greater than 1, so you got this mass cancelling, you got V by C. So when X is much greater than 1, X is much less than 1, V is much smaller than C, is a non-relativistic. But as X approaches 1, V goes to C.
So it's not greater than C.
No, it won't be greater than C, sorry. No, it won't be X is approaching. It's not, I mean, I like to say something like that. So it's not. Any other question?
Can you explain again why the free path is large for the electron?
Sorry, I can't hear you.
Can you explain again why the mean free path for electrons is large in the white hole?
Oh, that's because, because it's all degenerate. So how will an electron lose energy? So you see, no, it is like this. If an electron is scattered, okay, so it will have to exchange energy with itself. Right? But for that, then it will have to go to a lower energy state. But the lower energy states are all filled up.
So you are talking about the electrons that are not in lower energy.
No. See, you've got electron cloud, right? And then all the momentum things are filled up. Now, if two electrons have to interact with each other, they'll have to exchange momentum. Okay, but then what will happen is that when if for example, let's say what happens in a normal case, an electron which is going will sort of interact with matter, and then it can lose energy. But here, the lower energy states are all filled. Okay, so when you talk about the cross section for an interaction, the probability of interaction, it is a cross section into the available phase space. Okay, when you look at all the QED information. Now the available space here is all filled. Okay, so there is nowhere for the electrons to go. Right? I mean, I can give you, if you come to me, I can give you the more detailed thing which you can.
But there is nowhere to go.
No, so it just keeps on going forward because it is essentially not interacting. Right? It's not interacting because if it interacts, it loses energy. But loses energy, it should go to lower energy state, but that is failed. Right?
Sir, I read somewhere like if the mass of white rock increases, then their size shrinks. So, like, why it happens?
No, I did not say that the mass of a white dwarf will decrease or increase. I'm just considering white dwarfs with different masses. Okay, see, once you form a white dwarf, the only way in which you can change its mass is by putting matter. Okay, so I'm just saying that I'm considering a sequence of white dwarfs. Okay, so which have got increasing mass. And then in that sequence, the increasing mass corresponds to decreasing radius. I'm not considering a white dwarf actually losing or gaining.
Actually, that was written that it is a property of white dwarf. Like if we, like I read somewhere in Google, like if we put mass on the white dwarf now, then they shrink.
Yes, then so all right. You look at it this way: when you actually add, see, you've got this white dwarf, and now it is accreting matter. Okay, when it accretes, I told you that it's a binary system, so it is getting matter from other stuff. Right, so the mass of the white dwarf is increasing, and therefore it will definitely shrink in size. So why will it shrink in size? So that is because the gravity is increasing there. Okay, because the mass is, and that gets it to readjust in size. Because when it shrinks in size, the pressure will go up, the degeneracy pressure goes up. Consider degeneracy pressure, see it is like this. So P is proportional to the rho to the pi by. Agree? Okay, so now I got a white dwarf with a fixed mass and a fixed radius. Now I am adding matter to it, quite a lot of matter. When I add matter to it, you agree with me that the gravitational attraction will increase, right? So it will start, because the gravitational attraction increases, it will start shrinking. But as it shrinks, the density will increase, so the pressure will go. So a new equilibrium will be at a smaller radius. So if I continuously slowly add matter to it, then it will go on slowly increasing in mass, increasing in density, and decreasing in density.
Does it mean that the white dwarfs that are not in binary system will remain?
Yes, they will just maintain the same mass. And then they just keep cooling.
They won't go into super.
No, nothing will happen. They just keep cooling. So it is, I mean, just imagine if you exist for billions of years, what will happen? So it is like that. There's nothing else to do except to cool.
Is it possible for a white dwarf in a binary system to accrete enough matter and reach a state of neutrons?
You see, what happens is the following. I told you that it explodes. I mean, it thinks that it explodes. Now, people used to think that you can form a neutron star. But apparently, the current understanding is that that is not possible. There will be complete configuration. Okay? It just explodes completely. But these are all very difficult things. So they change with time, meaning that sometimes people say one thing. So you could in principle form a neutron star. But apparently the more likely is that it just explodes.
So, is there a reason why type 1 is supernova explode with the luminosity of that?
With that fixed luminosity, that's because the fixed energy is big. Isn't it? See, so see, it is like this. So you have to lock your mind to the existence of a Chandrasekhar limit, which is 1.4 solar masses. Right? So you see that when you form the thing, so you add a little matter, it does improve. And it always implodes at n is equal to 1.4 times solar masses. So the binding energy which is released is corresponds to that energy. So it's a fixed energy. Yesterday, somebody asked me about the mass function. Who asked me about the mass function? You asked me about the mass function. So actually, I'll just show you very briefly. If you like, I can. Maybe the next lecture.
Yeah, we have to do that.
What time is it?
Yeah,
We have a break now.
Oh, you're good. I have to go now actually. So we will see. You see here, this one. So this is what you observationally can do. And you see the cyanide that creates the problem. But under certain circumstances, you can the two components, you can get two of these functions. And if you divide one by the cyanide, okay? Yeah. No, there are no questions in chat. Yeah.
This one. In the table which you showed for the Chandrasekhar's calculation, I think at the top it was 5.7 solar masses.
Yes.
Why?
No, that's because it is not actually the mass, it's something else. But Chandrasekhar had got the mass wrong, okay, because he had made some wrong assumptions. Meaning they put in wrong constants. Not wrong constants, something to do with, I forgot the one. So the mass that he had got is this. Then the correct consider. Okay, thank you very much, everybody. So tomorrow, I'll talk about supermassive black holes.
So when a white dwarf is accreting matter, is there a possibility that the fusion of atoms will start again because the pressure?
You won't get much fusion there, but there are probably trace amounts of fusion. Not very much fusion. So you all agree with me that white dwarfs are interesting. There's a lot of active research going on.